Well, thank you very much, Esteban. So first of all, thank you very much for all of you who came to attend. And I deeply appreciate also this initiative to keep this webinar series going, because it really kept the ionic liquids community connected during this past year or something. And I think this was really wonderful. And because we didn't have the usual conferences going on, and IMIL was one of the more interesting initiatives allowing us to keep in touch. So thank you very much and congratulations for that. Very, very highly appreciated. In 2023, we'll organize the COIL meeting here in Lyon. And so we'll start activating this very soon. So looking forward to going back to live conferences. Yeah. So, but thank you very much. So today I'll be speaking to you about simulation of ionic liquids and DES using polarizable models and what we learned about the systems. So, you know, from my perspective. So I'm in Lyon, as Esteban told you. So Lyon is somewhere in the, you can say, the southeast of France, not far from Switzerland and from Italy, near Grenoble, another city. And Lyon is a very beautiful city. It's a World Heritage Site from UNESCO. It has a very nice old town and is the confluence of two rivers. One is the Rhone River, which is well known for the wine that is produced. And so it's a very important city for French cuisine. And there are very, very good restaurants and typical small joints where you can have local food, which is called the bouchon. And so it's very good standard of living, right? Good wine, good food. So. And Lyon is one of the main centers of chemistry in France and in Europe. So they call it the chemistry valley. And historically, it's, I think, because silk was a very big industry in the centuries ago. And then all these textiles and coloring and, you know, dyes, then it became chemistry. And so we have it's a big site in terms of chemistry, the Rhone Valley. Yeah. So with lots of innovation going on and biotech, etc. And where I work is the ENS, so this École Normale, which is a small institution. So we have a small intake of students and with a very tough selection. And but research-wise, it's large. So it has a huge number of big labs for research in sciences and humanities. And these two parts moved to Lyon some decades ago. They were formerly in the outskirts of Paris. They existed since the 1800 and something, 1870 or something. But those parts of this École Normale moved to Lyon in order for everything not to be in Paris. So this is political decision, but it's very interesting because it's a research-intensive institution and with very good students. So it's a real pleasure to work here. We have two campuses nearby, just almost across the street. And this is the group, the IL group, which is in the chemistry lab. Yeah, so you can see our website, and it's a very international group. So I'll talk about this molecular simulation of ionic liquids, and I'll try to keep the talk general, and so it's not for specialists. And so I'll start with this slide, which I've shown many, many times, which for me captures some of the essence of what are these ionic media. You know, for me, ionic liquids, as long as they are dominated by this ionic nature, they have pretty much similar physical chemistry going on, right? The solvation, the structure, the dynamics will be relatable between those. And I think the plot on the left is work of Luis Paulo about the cohesive energy of ionic liquids. And you see the red and green bars tell us about the electrostatic Coulombic contribution and the van der Waals contribution. And you see there's a balance. So ionic liquids are not simply molten salts, where everything is due to Coulomb interaction. They have these long tails, they have this relocalization of charge. And so there is a balance. And this balance is a delicate thing, right? And you see it again when you increase the side chain and look at melting points. So this is a plot by Ken Seddon, one of the pioneers of the field. And you see that the melting point is low for intermediate length, which is when you have this balance, right? Because short length of the side chain, you have a molten salt, and along you have a tensioactive, an ionic tensioactive, and it's in between that you have interesting features. And this in between comes again to this balance. So you have to have a good description of the interactions in order to capture what makes an ionic liquid or a DES an interesting medium. So it's a sophisticated thing. And of course, it's in the basic domain of sustainable chemistry that we are thinking about using these compounds. And of course, they were rather novel 20 years ago. So there was no previous experimental knowledge. And so the role of computational studies of ionic liquids and DES has been very important, because it's not like there was a huge body of experimental knowledge and then we needed just to have some microscopic view. So that's still true. So one of the roles of computational studies is to provide this molecular level understanding of the properties that we measure experimentally, macroscopic properties. But because of this lack of previous knowledge, computational studies have been a discovery tool of new features that were found in silico, and also a design tool, which is be able to use the tools of computational physical chemistry to design ionic liquids for application. So I think this is quite interesting, and it's quite modern in a field that to have these experiments and computational part going side by side. And I can give you a few examples of things that were discovered using simulation. So this is one of mine with colleagues, which is this heterogeneous and segregated structure of ionic liquids, where you have domains of aggregation of the nonpolar part, the side chains, and domains where you have the ionic head groups. And this was something that was found using computation and then later validated using experiment. Another one, which I think was a very interesting contribution, is the understanding of ionic motion, because there were lots of ideas about how an ionic liquid works based on ion pairing. And so how come the conductivity from impedance is lower than the conductivity that we estimate by the Nernst-Einstein equation from NMR? Means all ions are not available to conduct electricity. But of course, so this you can think about as ion pairs, right? So this is a simplistic view of what's going on. And Claudio Margulis, in a very interesting paper, explains clearly that correlations in ionic motion are not necessarily connected to ion pairing. Of course, you have, when you move on a cation to the right, you have to move an anion to the right to keep electron neutrality, but they don't have to be connected, they don't have to be a pair. And so this was very interesting analysis and from computational field that really provided a very interesting knowledge about dynamics in ionic media. And of course, there is a very interesting body of work on the design of ionic liquids for the capture of CO2 by the groups in Notre Dame, John Brennecke, Bill Schneider, and Ed McGinn, etc. And also there, a good example of how computational methods help design ionic liquids for an application. Right, so what I want to come to is that in order to be able to design these media, to do new processes, new materials, we need to understand their physical chemistry. And there the challenge is to describe the weak interactions, because you remember the subtlety of how much is Coulomb, how much is van der Waals, how much is flexibility, delocalization. So we have to have a detailed description. If not, with very simplistic models, we won't be able to do this design. And then, of course, ionic liquids and DES provide chemical platforms that we can that can be tuned. So we can change the molecular structure by adding functional groups, by adding head groups, side chain, etc., by the choice of ions, by the choice of hydrogen bonding, H bonding partners in DES, etc. So this has such a variety of structures and interactions, that is a problem, because we need to be able to describe a huge variety of structures and interactions, and that's not easy to do. We are talking about a huge universe in terms of chemical structures. And then the field is not so new anymore. So we are, the field is 2 decades old, if you want. And so now we must aim for more than just basic understanding of standard ionic liquids, of the middle of the road ionic liquids. So we need to go to optimize the performance, the cost, the environmental impact. So the specifications today are more demanding than they were in the beginning, right? So we cannot just come up with the ionic liquid, which is not green, right? And of course, so these challenges bump into a difficulty, which is how to describe the interactions. And this has been already pointed out 40 years ago by John Rawlinson, who was a very good physical chemist, thermodynamicist, who said that already in that time, 40 years ago, it was not so much what we don't know about the liquid phase or statistical mechanics or molecular simulation. Our problem was how to describe the molecular interactions, those weak interactions. Yeah, and so this is still today true. Still today is the difficult part is describing the interactions, and so that's where basically the group has worked to improve the description of interactions in ionic liquids and DES. So the big scheme of things is this multi-scale idea about computational methods or molecular modeling, if you want. And so we can do quantum mechanics at very short scales of time and space. So we can represent a few ion pairs. Here I'm talking about condensed phase. So I'm talking about the liquid state. I'm not talking about doing quantum chemistry on isolated molecules. So that's another different field. And I think you don't really represent the structure and the entropy and the ordering and the dynamics of a liquid phase by doing those kinds of studies. They are useful for many things, but I'm talking about representing the liquid state, right? So you can do that for a few ion pairs, you know, we'll see an example. But I mean, if you want to go to larger scales in time and space, in order to represent diffusion, in order to represent long-range structure, you have to abandon representing electrons explicitly. So you can no longer do Schrödinger equation. So then you have to have some simplified model where each atom is a site, and that's the smallest entity that you have in your simulation. And so you can go up to a certain scale with that kind of representation. And then if you want to go beyond that to represent liquid crystals or things that are really structured on a very long range and are very slow, you have to abandon the atomistic detail and use some coarse grains, which represents, I don't know, the full head group of imidazolium cation by just one site. And that's, you lose detail about hydrogen bonding, etc., but you reach much further timescales, etc. So there's the right choice of method for depending on the question. Yeah, but it's very important to have this in mind, that one scale of description doesn't do everything. So historically, I would say that in 2002, these fixed charge models became the standard where each atom is represented by an interaction site with a certain partial charge. And that's how you represent a molecule. And so it was Ruth Linden Bell, etc., who started that. And then a bit later, people understood that they were not very good for transport properties and decided to work with smaller charges on the ions. So ions, instead of being plus or minus 1, were treated as plus or minus 0.8. And that improved the dynamics. So those are charge scaling models. But it took a long time to go beyond that. And of course, there were efforts before 2017, but not sufficiently general for people to have a description of the interactions that goes beyond the fixed charge model. And so that came up a few years ago. And later, only very recently, we have really a transferable coarse grain model, which is the Martini force field. It's a very interesting one. I'll talk about it a little more. And it's quite recent, you know, a couple of years, last year. Yeah. And parallel to this timeline of using molecular models to represent the ionic liquids and the DES, there has been a parallel route of doing ab initio calculations. So this quantum mechanics, and it's basically since 2012 that these have been productive, reasonable to use. Before that, it was very slow because computers were not that good. But I think in the last almost 10 years, they became much more usable and they provide information at a more detailed scale. Right. So a bit about these ab initio methods. So you really are solving Schrödinger equation for the valence electrons of the whole system, of the whole liquid, and in periodic boundary conditions, if you want. But it's only very small systems. So here is an example of a DES, which is choline chloride, ethylene glycol, and with water. And you can see that you can run it for 50, 100 picoseconds. So this is very short time scale. And you have around 30 ion pairs and 30 ethylene glycol. So this is, I don't know, so a few dozens of molecules for a few picoseconds. And I mean, you can observe things at a local scale, the hydrogen bonding, very important to learn about hydrogen bonding and local structure. But you cannot really, it's very hard to get to diffusion coefficients or things like that because you only have a very short observation time. But very interesting for quasi-chemical effects. Because you are solving the equations for the electrons, you see all these induction, polarization, charge transfer. So it's very useful for those to observe this kind of behavior. At mid-scale, you have the molecular force field, right? So this is a simplification, of course. So it's an equation that tells you how these atoms interact. Can be through bonds, covalent bonds, can be through angles where the angles in the molecule they bend, torsions where you have the conformations because molecules are flexible and they have the conformation. So you need parameters for all that. And this blue part is the intramolecular part, basically. And all the parameters you can get from quantum mechanics these days quite well. So this is pretty much standard stuff. The hard part is the non-bonded interaction, so the van der Waals forces. And those still today are obtained empirically in most cases, because it's from thermodynamic information that you have the sensitivity to these very weak interactions. If you want to calculate them, you have to go below 1 kilojoule per mole. And that's very, very difficult for quantum chemistry calculations. Yes, so you're really looking for electron correlation effects, polarization effects that are below 1 kilojoule per mole. And so very hard to do from first principles. Charges are not so difficult to get from first principles, but you know, partial charges are point charges are something that only exists in our mind. So molecules don't have partial charges. They have a nuclei and electron clouds, and partial charges are an assumption which is not very good actually. You know, the negative charge is smeared out. It's an electron cloud. So So one important thing is that if you are developing parameters for the equation I just shown for a wide variety of compounds, it's very useful if you can transfer them. If the same functional group can retain its parameters when you place it in different ions or in different molecules. So this is very important in order to have a tool that covers new compounds just by assembling the fragments and building a new ion or a new molecule. So this transferability of the model is key. And it's sometimes worth sacrificing some specific performance for a given molecule or even for a given family of molecules in order to have a model that covers a variety of compounds and can describe compounds that you have no information about. So this is very important to have this kind of fragment approach. And so this was the model that I worked on for many years, since 2004, 2006. And it's the CLNP model, right? So you can download it and you can use it. So many people use it, and I'm happy to always provide help for users of the model and people in the group as well. Coarse grain models. I mean, here each site represents many atoms, 6, 8, whatever. And they are very good to work on phase transitions, on mesoscopic behavior of mesophases, liquid crystals, aggregation, etc. But of course, you lose detail of specific interactions. You lose detail of charge distributions. You lose detail of hydrogen bonds. But you have to do the best you can. And this Martini force field is fragment-based too. So you can reuse the beads to build new ions, build new molecules. And so it also follows this fragment approach. And that's why it's useful, because you're not stuck to just one family of compounds. You can use the Martini model, mixing ionic liquids with proteins, with cellulose, with whatever, water. You're not stuck to just one family of compounds. Very recent, yeah. Now, Martini has been around for a long time, but for ionic liquids is recent. So what we do today in the group is basically move to a new generation of model where we represent this polarization. We represent the fact that the electron clouds respond to the local environment, and we no longer have fixed charge on the model. So what was the problem? The problem was that with a fixed charge model, the previous force field, the structure we think was okay, but the dynamics was pretty bad. So you can see here that density is close to experiment for some ionic liquid. And then diffusion coefficients are very low, viscosity very high. So this was the main problem, that it was a good model for structure and not good for the transport properties. Of course, then I told you that people thought about reducing the charges to improve the dynamics. Of course, it works because you are reducing the cohesive energy. And of course, you see that the first peak on the radial distribution function. So this is the probability of finding atoms at a certain distance, if you want. So the first solvation shell is the first peak. You see the maximum on the first peak moves a little further away, which means that the density goes down. Of course, you reduce the cohesive energy, the density goes down. So the density will be underestimated. It's the price you have to pay to have better transport properties. So this is sort of a quick fix. People say, oh, this represents polarization effects, charge transfer, etc. But I think it's really just a quick fix to a problem that creates another. And so we have to move beyond this idea of having fixed charges, because we can improve on the representation of these subtle interactions. Because, of course, when we have a pi system on imidazolium ring, or we have atoms with loose electrons, double bonds, etc., these respond to polar molecules or other ions around. And so the center of negative charge, the electron cloud, moves with respect to where the nuclei are. to the molecule. So to represent this induction effect, give some degrees of freedom that represent the electron clouds. And polarizable model can do structure and dynamics better. There are many ways. So this is like a bit of a overview of how can you achieve this. So you can achieve this polarization. So this fact that the electron cloud is displaced from the center of the atom by the effect of some nearby charges. You can achieve that by just fluctuating charges. Changing the value of the charges means that on the molecule, charges go down here, they go up over there. So it's like the electron cloud was displaced in the molecular skeleton, if you want. You can do that by adding point dipoles, which appear on each atom according to the local electrostatic field. So the atom contains a charge, but it also contains a point dipole. And this dipole is calculated on the fly according to the polarizability of the atom and according to the local environment. So this is one way to do it. And there is another way to do it, which is two charges with a spring, and they can move away from each other to create this induced dipole to respond to the local electrostatic environment. So both are quite similar. The advantages of the induced dipoles, it's mathematically probably more accurate, but you have to simulate dipoles. It's not very friendly for a molecular dynamics code. You add dipoles in there, and the dynamics code wants to see point charges, point sites, and springs, and all things that are mechanically easy to handle. So through the induced dipoles, if the charges don't move a lot, seen from afar, it's like it was a point dipole. So it's a good representation of induced dipoles. Of course, you can, what you should do theoretically is at each time step of the simulation, at each configuration of the system, you move your atoms, and then you iterate all the induced dipoles or fluctuating charges to minimize the energy, so that you relax them to minimize the energy of the system. And that's what a self-consistent method would be to give the exact answer of the energy of the Hamiltonian for that system. But this is a pain because you don't want to have an iterative loop at each time step, because this is heavy computationally. So people use a trick, which is to sort of treat these fluctuating dipoles or charges as additional dynamic degrees of freedom. So this is already a trick. And then the result is this. So you have something like, so you can see the white dots are these Drude particles. And I mean, you don't see them vibrating a lot around the atoms. They stay very close, but they represent these induced dipoles. So the induced dipole is given by the polarizability alpha, which is the proportionality between the induced dipole and the applied field due to the other molecules. And it's this alpha that determines how much charge goes on these two particles and what is the force constant of this spring keeping them together. So there are no parameters except this polarizability. So in principle, we have an additional parameter to the force field, which is the polarizability of the atom. But otherwise, we don't have any fudge factors. We don't have any much empirical things at first sight, right? So, but in truth, this is not so. But it should be physically sound. We just need to know the polarizability to know how much charge and to put on these particles. Then once you understand this, then you start realizing that the devil is in the details. So the first detail, which is a technical detail, which is crucial, is that you cannot, so you put a mass on these particles that are attached by a spring. So these things will suck kinetic energy out of your system because they want to reach the equilibrium with the temperature that you impose. But you don't want that because they really represent the electron clouds that are massless in the spirit of your molecular dynamics. So there is a trick, which is to keep this motion of the Drude particles cold, so that the trajectory that is obtained is very similar to the one that I would obtain by equilibrating, by iterating and doing this energy minimization, right? So in order for the system to work, for this scheme to work, it's important that the motion of these Drude dipoles is kept very cold, so that they are near equilibrium distance all the time. And so this is a big trick in terms of thermostats in your simulation, and you have to make sure that the center of mass motion of the molecules, that the intramolecular modes, intramolecular degrees of freedom, the vibrations, the torsions are at the temperature that you want, so 300 Kelvin, and that this temperature is the temperature that you ask, and that you are not losing kinetic energy to these cold degrees of freedom. So this is a crucial step, and it's a lot of work on the thermostats of the molecular dynamics to be able to do that. So then another dirty trick that you need is that when you have very strong hydrogen bonds, you can have the Drude particle being pulled away by some positive ion, if you have lithium or sodium in your system, if you have a very strong and persistent hydrogen bond, like the intramolecular hydrogen bond in ethylene glycol, you have risks that the Drude particle is pulled by a nearby positive atom. And so this is because the scales are so small that you can no longer afford to have point charges. You need to smear out these point charges to represent the electron clouds. So you are too close. And so there is a physically sound way to do this smearing. So it's not done purely empirically. So there is a reason to do that. It's called the Tolle dumping. And Tolle was a researcher who worked on these problems. And so, which means that your electrostatic interaction no longer diverges at very short range. So we are of the order of 1 angstrom, whereas carbon atom is like 3 angstroms yeah. So this is at very short range. When you have this strong hydrogen, etc., the Coulomb interaction is damped so that it does not diverge in order to avoid this problem. So this is sort of a safeguard so that the trajectory is stable. So you see that although we don't have many empirical parameters and fudge factors, there are quite a few technicalities into running a polarizable model. And this is something that if you want to try them, you have to be aware that there is a learning curve, and it's more sophisticated than a typical molecular simulation, right? So then, as I told you, there is a huge database of parameters for the fixed charge model that describe many families of ionic liquids, of pairs, etc. And we want to add this polarization term, but without having to recalculate everything. So we don't want to reparameterize the whole thing because it's a waste of time. It's going back 20 or more years that we have to go back to the parameters of all the functional groups, etc. So what we want is to reuse what we already have in the fixed charge model and just add the polarization to it. And so so I have a hand raised, but I think I'll leave questions to the end, right? I'll leave questions to the end.
Yes, at the end, we will have room for questions. Okay,
good. So if you think about your interaction potential, which is this black curve, what we want to, so this is the overall interaction between two ions, if you want, or an ion and a molecule. So what we want is to have an explicit representation of the polarization, which is the green part. So the green part, so we can decompose the total interaction into contributions: electrostatics, repulsion, polarization, dispersion, and then the total, right? So what we want to do with those induced dipoles is just the green part. So this contribution. The rest is there done by other terms in the model. The charges do the electrostatics, the Lennard-Jones terms, they have to do just the dispersion and not everything. Okay, so what we want is to scale down the Lennard-Jones potentials so that they become purely the dispersive part and the repulsive part. And we wanted to take out what was there implicitly, because that will be represented by the induced dipoles explicitly now. Okay, so what we want is to rescale the old model so that now we can have polarization explicitly represented. And this is done by doing this energy decomposition with a quantum chemistry technique, which is SAPT, allows us to calculate what's the part of the dispersion. It's typically 60% or 40%, doesn't matter. And so we have those numbers for all those functional groups, for all those fragments. And we even have a correlation to get those numbers if we don't want to do the expensive SAPT calculations, because those are computationally intensive. So with that modification, we have the new model, this CL and Pol, which is a model that is now polarizable. Yeah. And so it describes structure quite differently. So if you compare the fixed charge model, you had several solvation shells which were very well defined. So these are isoprobability contours. And on the polarizable model, you keep the first shell, but you lose a lot of correlations beyond the second shell, which this is why the dynamics is better and the structure is not lost. Whereas in scaled charges, you lose a bit of the structure already from the first solvation shell. So we understood what is the effect of polarization on structure. And we also learned that the transport properties are much more robust. So we have very reasonable numbers and good composition dependence of transport properties, for example, in sodium electrolytes, which with the fixed charge force field were a bit anomalous, right? So I'm not going into the details, but so we have better representation of structure and dynamics. So now a few examples. So all these I'm going to show now are examples of work done with the polarizable model. So if you go to protic ionic liquids, so this ethyl ammonium nitrate, so EAN, it's very interesting because it's a bit like water, a liquid dominated by a network of hydrogen bonds. It's a very interesting molten salt, protic. And it's interesting that in the literature, there were two conflicting views about the hydrogen bond network. So are the hydrogen bonds linear, like NHO being linear? So short distance, 1.9 angstroms, and an angle of almost 180 degrees, so 165, or are they bent, like 2.4 angstroms and 120 degrees? So you had information on both. So some people said it's linear from ab initio calculations, from clusters, from the crystal structure. All these said, oh, it's linear. And then you also had people doing neutron and X-ray scattering in the liquid phase, and then going back to the interaction potential with some refinement scheme, said it's bent, right? So they would say it's bent. And so there's this discussion in the literature, and we thought it's very interesting. So if you run it with our new polarizable model, it's linear. So we have, you can see here, the distance is 1.9, and the angle is about 165. So this is perfect agreement with the linear H bond. And of course, if we tweak the model, if we change some sites, and it's possible to make it bent, but in honesty, what the polarizable model predicts is linear. So for us, this is very interesting how to use this model, that we are very confident on how it reproduces structure. And so it's my bet is on the linear. And if we take the model and calculate the X-ray and Newton diffraction, which can be calculated from the molecular dynamics, we have something which is good. I mean, which means that if you have X-ray and Newton scattering and want to go back to the interactions and the details, it's not so easy, because you have several patterns that will give very similar diffraction patterns experimentally, right? So it's very difficult to go the other way around. And you have to have very good molecular models to be confident about this. So our force field is not completely out when you try to reproduce the experimental neutron and X-ray scattering. Right. So next, charged interfaces. So we use the model to study ionic liquids as electrolytes for transistors, when you use the ionic liquid as a gate to polarize and to improve the charge carriers on semiconductors like MOS2. So I show you this because it's already a composite system. It has an interface with a solid 2D material, and everything is treated with polarizable model, both the ionic liquid and also the polarization of the electrodes, because the charge on the electrodes will depend on what ions are close by. So the material is also described with a polarizable model. And of course, so what we learned, many interesting things connected to work we do using AFM with collaborators to study the interfacial layers and how this works. So we learned about how the ions organize at the surface and how, for example, the different applied voltages, here is the angle of the side chain of octylimidazoleum with the surface. We can see that at 0 volts, so no applied potential. So this is the density profile. So it's symmetric between the two electrodes because there is no applied voltage. We see the side chains are low angle, so they are basically parallel to the surface. And when 2 volts are applied, we have segregation of anions going to one side, cations going to the other, and the structuring is quite different. So we can analyze the nature of these interfacial layers with the charged interfaces. And some side chains, you see, take angles now about 70 degrees. So you have a completely change in the orientation. And we are studying how this affects the capacitance, the charging. So how to design the electrolyte to have the properties that we want to do these devices. So how to design the ionic liquid to do this. Another study which I found very interesting with the polarizable model is to study the gas absorption, which is a big topic in the group, and thinking about the entropic part, which is defined by free volume, and the interaction part, which is due to the strength of interactions. And of course, you can quantify free volume in ionic liquids using simulation, because you can analyze the bits of empty volume there. And although there is not much of it in ionic liquids because they are very cohesive, you can. So this is a project in collaboration with Edwards Bakis from Latvia, who synthesized this set of ionic liquids with the silicone atoms there in the side groups. So it's not something that brings polarity to the side chains, but it brings something which is different from just hydrocarbon side chains. Different volume, different flexibility, and hopefully different free volume in the ionic liquids. So you can see that if you look at cavities of different size that spontaneously exist in the ionic liquid, so of course you have a lot of small cavities and just a few big ones. But how much do they define the solubility of some non-polar gases? So the study, you can see this is the order at which we find free volume. So if you look at the size of a typical gas like argon or something, the order at which you have free volume, larger and smaller amount of free volume is the way it's shown. And it matches the solubility. So here we have a view of something that we often don't pay attention in ionic liquids because they are not very compressible and we think they don't have a free volume, but they have a little bit. And it's enough to be the deciding factor on the solubility of non-polar gases, right? So this is something, if you want to think about selectivity, etc., this is an interesting argument. So both on the structure of the cation and on the structure of the anion. So if we look at different anions, also the solubility correlates with the free volume available. So this is something that we were very happy to see, that the force field is being consistent and giving us this view on the free volume available in the ionic liquid. Final example, so about porous ionic liquids, where we have particles of MOF, which is a porous solid, suspended in an ionic liquid in such a way that the ionic liquid doesn't go inside the pores. So for that, we need large ions. So we took these phosphonium ions, P66614 with some anion, and it doesn't really matter very much. But so the phosphonium ions don't enter the pores of the MOF, so they stay out. So you have a suspension of empty particles, highly porous, that are stable in the ionic liquid. And if you do the X-ray scattering, you see the peak and the pre-peak of the liquid. This is typical of the long-range ordering of the ionic liquid. So this peak number 1, 3 is the cation anion charge ordering, right? And on top of that, you see the spikes of the crystal structure of the MOF, meaning that in the suspension you really have MOF and ionic liquid, both, and you're not destroying the structure of the MOF, right? So you have a porous liquid. And so porous liquid in simulation, we have some studies where we have real particles, but the ones I'm just showing have a slab of MOF, so you can see what the MOF looks like. It has these hemispheres, and these where inside there are spherical cavities where small molecules can access, but the ionic liquid does not. So the ionic liquid stays on the outside, and so the simulation system has part of ionic liquid, part of MOF, and then again the ionic liquid, because it's a periodic box, right? And what we are studying is what happens with the CO2. So can we increase the solubility of CO2 in these systems? And of course, the simulation is very interesting to understand the structure of the ionic liquid near the MOF, how much the side chains can probe into the cavity volume, etc. CO2, does it diffuse across the system? Where is it more soluble? Is it in the MOF or in the ionic liquid? Can it react with other compounds dissolved in the system? So these are large systems, large simulations of 70,000 atoms with many ion pairs, a big amount of MOF, several CO2 molecules. And so this is typically the size of the system that you can do with a polarizable model. So this is quite challenging because you have the MOF is fully flexible. It's also described by a polarizable model. So it's sort of the largest systems we tend to do in the group. And of course, you can have several properties. So you see here that the density of CO2 as a function of the coordinate along the box, there is a higher concentration of CO2, which is the blue line in the MOF than in the ionic liquid. So here the MOF particle works as a reservoir of ionic liquid that's stored in this porous liquid. So it enhances the absorption of CO2 by the solvent, if you want. So I hope I gave you a few illustrations of how the new force field works and the systems that it's possible to model with it. And this was possible because we have access to computational tools, and most of the software is is free and is open to the community to use and to contribute. And this is something that we are lucky to have, this open source development. So all the packages I use are mostly open source, and we contribute to them as well. And the work was run on the computing center of our school, and also on a big computing center of the CNRS. Yeah, but the one in our school is very big too. So these are the resources that made it possible, and of course the people. So Edwards, Inez, and Jocasta participated in these examples through the experimental part, measuring solubilities or X-ray diffraction, etc. And Katya, Zhang, and Ryan were the heavy lifters doing the simulation work on the different illustrations that I showed. And of course, Margarita is co-PI in the group. So that's it. Thank you very much. Sorry if I took a bit longer than I was expecting. Open to questions.
Well, thank you very much for this wonderful presentation, Professor Agilio. I think it was really nice presentation. No worries about the time. Huh? Well, the stage is open for questions, so you can switch on your microphone and ask directly Professor Agilio, or you can raise your hand and we give you the stage. Also, you can write down your question in the chat and we can read it for you.
Yeah, I'm reading the chat.
Okay.
Professor Rio asked a question before in the middle of the presentation. I don't know if he's here.
Okay, the stage is open for questions.
Okay. Am I allowed to ask something?
Yeah, of course.
Well, first of all, congratulations, Agilio, for, as usual, a fantastic presentation. In fact, you have ruined many of my questions, although I'm not a specialist, as you know, on any kind of simulations, but you were able to explain to a guy that does not know much about that. I still have a doubt, be it in a polarizable or non-polarizable models. How do you treat the hydrogen atom? Is it
Right.
a point?
Yeah.
Is
so
it...
So let me try to get there. So the question is that you have to put a mass on this. A polarizable atom gains an additional particle, which carries negative charge. And we put a mass there to treat it as a dynamic degree of freedom. And that's why then its temperature has to be kept cold, blah, blah, blah. So if that mass is about 0.4 of atomic mass unit. So if we put that on a hydrogen, it's a big perturbation to the hydrogen, yeah? And also hydrogens have low electron density. So we prefer not to treat hydrogens as polarizable atoms. We put the Drude particle on the carbon or the oxygen or the nitrogen or whatever. So we put the Drude particle on the heavy atom to which the hydrogen is connected, but we sum the polarizability of all the hydrogens. So a CH3 group has the polarizability of carbon plus 3 hydrogens, but it only has one Drude, one induced dipole. So we are treating the induced dipoles in a sort of we are coarse graining it a little bit because it's too much to go and put polarization particles on hydrogens. These two reasons: the mass is too small and the electron density is too small. And so some models have induced dipole on hydrogens. Some water models have that. But if you want to go to bigger molecules and ions, this is too expensive and too complicated. So we think about, CH2 group, CH3 group, NH3, etc., as just one polarizable site, but 4 atoms or 3 atoms, etc. So they're described like that. Good question.
Okay.
We have a question on the chat. Oh, please continue.
Okay. Well, the other thing I'd like to comment is I was very glad to see that the dynamics, the understanding of the dynamics, sensor properties, diffusion, viscosity, seem to me that have been improved a lot during the last few years. And that is a very important thing, I guess, because it was a previous failure, let's say, of of these MD simulations. Anyway, my question is, are you in general already confident in predicting by itself with no data? So I could give you, let's say, a combination of cation and anion, and I would ask you to give me your prediction at a given temperature, obviously, of the viscosity of that pair. Are you confident of that, or do you need experimental data to be confident?
Yeah, so when the first field was published, there was a training set and a test set, right? So we had a number of compounds on which we got this, right? So we have a sort of a training set and a test set, which are the empty points and the filled points. And you see there is no difference. So and each point represents a kind of fragment, sulfonate, imidazolium, pyrrolidinium, whatever. So we had a universe to start with, and within that universe we split it, and we said, okay, we'll learn from this and try to predict that. And we saw no structure, no correlation, so we were confident. And in many cases it works well, but there are surprises. So we had surprises when we have very strong hydrogen bonds, which were not on the training set. So then we learned about how to do the protic ionic liquids and the DES after. And now we know how to do the protic ionic liquids and the DES. So it's the generality and the transferability is good, but it's of course not absolute. And for example, lately we have a very interesting case with tetracyanoborate anion, because the tetracyanoborate anion has these cyano groups which are sort of dipolar, and the anions come close in a very strange way. And we are still thinking about. So for example, I can consider that tetracyanoborate may be a surprise around this path. And I don't know if we are very good at predicting the viscosity of tetracyanoborate, but in many cases it will work fine. Yeah. Okay.
So well, one last, because I don't wish to monopolize.
There's a danger
that your title has a deep eutectic solvents. I've not heard much about that, but it's not important because anyone, it's interaction. But what I'd like to know from you is what you think about, well, first of all, what is a deep eutectic solvent to you? and how different they can be from, you know, the standard ionic liquids, and how useful or not, because in fact you have a huge mixture of solvents, and so in separations and things like that, everything is complicated.
Yeah, so I mean, from this molecular modeling standpoint, what's different in DES is that they have a lot of hydrogen bonds with ions, and this makes the difference for the modeling. Otherwise, it's a mixture of organic salt with some molecular compound, but it's the hydrogen bonds with ions that are very strong and have a huge effect on this hydrogen bonding. And so once that was solved in the polarizable model, so we are okay for modeling DES. And we have a number of studies of DES with solvation in DES and DES for dyes, to dissolve dyes, to dissolve CO2, etc. So the DES problem was hydrogen bonding problem. And that's how they are different from the traditional non-protic ionic liquids. And they are similar to protic ionic liquids in a way.
Yeah.
The fact that it's a mixture with a molecular compound is not a problem. So that's handled quite well by the model. There was a question on the chat about the DES mixed with pharmaceutical compounds. So we have some publications about DES for the extraction of dyes and antioxidants, which are the same kind of big organic molecules. And it's okay, so it's fine. We're very happy with the results. So that's not a big hurdle. Yeah, so then I have another question that I see about page 25. So what's the R? So the R here is the distance between centers of mass of two fragments, right? So this is just this intermolecular potential between two fragments. We think in fragments so that then we can assemble them to make an ionic liquid or a DAS, etc. So you can think about benzene group is a fragment, alkyl chain is a fragment, imidazolium head group is a fragment. And we study these fragments independently. And when we have parameters for them, then we can use them to make the model for complex ions and molecules. So this is how we studied that we have a certain contribution of polarization, dispersion, etc. when we look at two fragments. Yeah.
Okay, thank you so much, and congrats again for all your work.
Yeah, thanks, Luis Paul. There's a question about homolumo orbitals in eutectic solvents as ILs. Right, so here we're not really studying the electronic structure. So the only representation we have of electronic structure is that we have some degrees of freedom that tell us how the electron cloud is polarized. So these models will not give you reactivity. So you don't have empty orbitals. You just have a very simplified representation of what's the electron clouds, but not the structure in terms of energy levels. So we don't have that. So I don't think of the story of the deep or not deep. For me, that's not a discussion, because what we want is something that is a liquid at room temperature. So we want to have a liquid medium that we can use as a solvent, as an electrolyte, a reaction medium, a lubricant, whatever. So we want to make a liquid out of an organic salt that unfortunately the melting point is too high. But it's cheap and available and non-toxic. So we want to make a liquid out of it, and we do it by mixing with something else. So for me, that's a DAS. And I don't think we should discuss if it's deep or not. It's irrelevant, in my opinion.
Okay. Yeah, one more question, the last question, I think. Professor Schroeder, if I pronounced correctly, you can switch on your microphone, I think. You are muted. Please switch on your microphone in the Zoom. No, your microphone is correct, but in
okay, yes.
Okay,
yes.
good.
The polarizability model used applies for weak, uniform electric fields. Now, in the molecules, you don't have this. So, I congratulate you certainly to the success, but nevertheless.
Yes, of course. So, I mean, so let's go to the big scheme of things. So, of course, this is a model. A model is also always a simplification, right? So, if you want to do explicit electronic structure and have all the details, it's very costly, and it's feasible for a certain scale of description. And then, developing interaction models and force fields is not exact science. It's not pure physics. It's a sort of, you have to have a certain flair to represent what's really important and forget about the other details because you cannot afford them. So, of course, if you go to the basic physics, you're very far, you're never happy. But I think that's the difference between physics and chemistry. Chemistry is more dirty, and then so you have somehow to, and engineering is even worse. So you have somehow to keep a sufficiently simple representation that you can live with, and so of course in this we can see the breakdown of the point charge approximation. When you are at short range and you have to smear those charges again. So you'll have the breakdown of all this, of pairwise additivity, which you already have. So when you go from a fixed charge model to polarizable model, you already abandoning the pairwise additivity, and you have a more sophisticated representation of interaction. So the interaction of A and B depends on C. It's not just a pair property. And this is a very huge jump in sophistication, which you didn't have before.
Well, it seems that for treating the hydrogen bonding, you had to do already something else, which is probably taking into account such nonlinear effects.
Of course, yeah. So it's true that here the hydrogen bond is inherited from physicists who like to put just a point charge and say a point charge in this represents the Coulomb interaction represents the hydrogen bond. So this is physics thinking. It's not chemistry thinking. But it's the simplest model that we have, and for structural properties is quite okay. So I mean, it's a big discussion, yeah. So about hydrogen bond and etc. Yeah.
Thank you.
Okay.
Anyway,
Wolfgang.
a great talk.
Okay. I'm agree with that. A very nice, very interesting, a great lecture, Professor Padua. Thank you very much again. Thank you for your time. And I don't know if you have last words for the Ibero-American community to finalize this presentation.
No, it's as I said in the beginning, I mean, I have to be thankful and to you in the name of, I think, the ionic liquids community and DES community because of keeping this event going, which I think in this pandemic situation kept a link between us. So thank you very much for that. So really appreciate it.
Well, thank you very much again, Professor Padua. Nice presentation, and we'll see you all next week. We will have another interesting webinar for you. Thank you very much again. Thank you for your attendance.
Yeah, thank you all.
Bye-bye.
Bye-bye.